Hello everyone. So our project is code vulnerability detection using graph learning approaches. So here is our team overfitters, me Mustavi Islam, Keenan Flynn, Eric, and Hoyun. Next. So we want to apply graph learning to assess the structure and control flow of a Java program in this project. So we classify Java programs using control flow graphs, CFG, and deep learning techniques depending on the type of code vulnerability or common weakness enumeration, CWE. For example, the buffer overflow present in the program. If there is any, so we can detect that. These vulnerabilities are often caused by subtle errors made by the programmers and can propagate quickly due to the prevalence of open source software and code reuses. Next. So increasing number of code vulnerabilities are discovered every year, whether they are reported publicly or discovered internally in a proprietary code. Code vulnerabilities are accountable for an average of 3.86 million in damages per breach. This is a stunning figure that would easily bankrupt a tiny business. If if any programmer can reduce the amount of vulnerabilities in code, malevolent organization will have a harder time breaking into the modern code system. Deep learning is responsible for detecting these type of vulnerabilities, often known as CWEs. Next.
So there have been previous approaches geared towards finding code vulnerabilities. Because code is a form of textual data, you have to use an NLP approach to the problem. This includes embedding sentences into vectors so that deep learning algorithms can be applied to the problem. Examples of these kind of deep learning algorithms include LSTMs and RNNs, but there's limitations to these networks being applied to programs because programs are not always ordered, and LSTMs and RNNs assume that the data is ordered. Take, for example, an if-else block. So there always will be a line of code that is not executed. And this is a limitation of recurrent neural networks because code is not always an ordered sequence. Next. So how do we represent this non-linearity of program sequences? Our solution is to use control flow graphs, which we refer to as CFGs. CFGs are an abstract representation of code, which are typically used by the compiler, and they follow a standard graph structure with nodes and edges where the edges are directed. Each node is a line of code, and each edge is a possible path of execution from each node. Take, for example, the graph below. If condition S2 is true, then the nodes on the right-hand side of the graph will never be executed. So this is where a linear approach fails and a graphical approach succeeds. Next slide. This figure is an abstract representation of our project. So our input is Java methods, which have been gathered over the web. The CFG converter converts the Java methods into control flow graphs. Our data set is then comprised of 10,000 of these control flow graphs, which are stored in .dot files, and they're split into training, testing, and validation subsets. They are then pre-processed and split into 3 subfiles: the edge file, label file, and node file. The node file is then embedded using a sentence transformer from BERT. Before entering the neural networks, they are then recombined into a non-readable .pt file, which was inspired by PyTorch's TU dataset class. And then we train the neural networks, the graph attention neural network, graph convolution neural network, and transformer convolution neural network, which are built and then trained and then evaluated with the test subset. Finally, our metric for this project is F1 score and accuracy. slide.
Here's the raw data of the control flow graph. We have already converted those original Java program into those control flow graph. Each node presented from the node label as the basic programming, the code sentences. We're converting these into 768 dimension vectors, which are those float vectors that presenting these single sentences. And then in the each subgraph of each cluster, which is those labels means the whole method name or maybe function names. And then in these each function names, we have like each node that in the sequence number presenting for the knowledge graph of this control flow graph. And then there's like from the adjacency of those edges, the node adjacency of those edges, we present in this way from the dot file. And how we store these how we store these files that the origin data is here. Just put it everything here into the dot file, which stored here. Like each CWE like vulnerability was stored here, and then we have a few non-vulnerable cases listed here. Why we split into so many non-vulnerable? Because like non-vulnerable have so many data that the dot file cannot be supported for over 10,000 at the same time. So that's why we split into 6 non-vulnerable data. And then for our for the converting those dot files to 3 different type of files, which is the .adj, .gf, and .ndf. We start in 3 ways because we have to make sure that the pre-processing works fine and have 100% true, 100% like accuracy of the converting data. So we put it every single data to the full, and then there's a raw folder, and then we have the ADJ graph label and node vector, 3 types of folders, and then I just created those different folder names that contains all the subgraph into single ADJ file. Like ADJ file is just the adjacency that represent those edges of those node relations. And for the graph labels, these are just using one hot vectors that like no matter how many classes we have, we just add one more digit to the one hot vector, so it's extensible. And finally, for the node vector, we're converting those all those data into 768. So which means every single sentence in the previous graph we showed, each sentence will be converted into 768 float, and then this is just the single one. For the first graph, like CWE, let's see the 015, we have in total of 9 nodes, which makes it 9 times 768 matrix. So that's why I have to divide it. We have to divide it those different data into 3 different types, and then after that we concatenate it to let the model know that we're gonna train these data.
So after training the 3 different models, here we have F1 score. The first of all, the graph attention neural network was around 91% of accuracy. And the next, the PPT bar. And then the second, the graph convolution neural network is around 85%, which was the lowest point. And then next. And then lastly, the transformer convolution neural network was around 93%, which we can verify this is the best model from these three models. Yeah. Next.
So in our future work, we will change the hyperparameters, like changing the number of neural layers. So as we have tried to get our best from this project, so yes, in the future we have a plan to perform more better to get the more better result. So that is why we'll explore other graph neural network algorithms which perform better than these ones. And here we use sentence transformer BERT as our word embedding. But in future, we'll examine that if there are any other word embeddings that can make good, better result than we have derived. So yeah, so in future, our plan is this.